Okay, I'll get right to it. Thanks for sticking around. So this is joint work with Michael Mitzenmacher and Jiayang Jiang. It's about peeling algorithms. So if all you get out of this talk is what is a peeling algorithm, I'll be perfectly happy. So a lot of algorithms in a wide variety of applications can be modeled in the following way. So you start with some random hypergraph G. And you just apply the following greedy process. So you repeatedly do the following. So while there exists a node V of degree strictly less than k, where k is some parameter of the algorithm, you remove V and all of its incident edges. And this removal may well create new nodes of degree strictly less than k, so you can just iterate. And at some point, you're either going to remove all of the nodes and you're done, or you'll get stuck. There are no nodes of degree less than k, and you can't go any further. Okay, if you get stuck, the remaining graph is called the k-core of G. And in most algorithmic applications, k equals 2. Not all, but most. And typically, the algorithm will succeed if the k-core is empty. We'll see some examples in a second. So the data structure underlying the algorithm will typically be deliberately designed to ensure that the k-core of this random graph is empty with high probability, because there'll be some failure mode otherwise if the k-core is not empty. And this typically yields very simple greedy algorithms that run in linear time. So let's see, let's illustrate this process just to make sure we all understand it, and then we'll see an example. So here is, this is not a hypergraph, it's a regular graph, or a simple graph, regular sort of overloaded in this case. And this is how peeling might go on this graph if we're going down to the 2-core. So you might identify this edge as being incident to a node less than 2, so we can remove that node and this edge. This, unfortunately, does not create any new nodes of degree less than 2, but there is another node of degree less than 2 already there, so we can identify that node and remove its incident edge. And this does create a new node of degree less than 2, so we can remove its incident edge, and that creates a new node of degree less than 2, so we can remove it, and then we're stuck. Okay. So in a simple graph, the k-core, the 2-core is non-empty if and only if there is a cycle. But in general hypergraphs, it's a more complicated object, the k-core. Okay, so let's see an example algorithm that is really doing peeling. So this is an algorithm for the sparse recovery problem, which is defined as follows. So consider a data stream that inserts and deletes a lot of items. So it's a turnstile stream, such as the graph streams that Andrew was just considering. And some other examples would be flows through a router, people entering and leaving a building, et cetera. So the sparse recovery problem is just to list all of the items with non-zero frequency. But typically, we want to do the listing not at all times, but only at off-peak times where the number of items currently residing in the stream that haven't been deleted is small. Okay, so if we do, let's say, n insertions in total and then n minus m deletions, and we want a list at the end, we only need to list the m items that remain. Okay, and we want the size of our data structure to be proportional to m, the working set size, the number of items that remain, and not to n. So think of n as very, very large and m as quite small. Okay, so this algorithms for this problem are a central primitive in more complicated streaming algorithms. For example, they're a central part of the L0 sampling algorithms that just appeared in Andrew's talk in several places. So is the problem definition clear? Okay. So here is an algorithm for sparse recovery. Just to make it simpler to present, I'm going to assume that no item has frequency more than 1 when listing occurs. It's very easy to modify the algorithm to work with higher frequencies, but just at the end of the stream, when you want to list all of the items that have not been deleted, let's assume everyone has frequency either 0 or 1. Okay. So this algorithm is called invertible Bloom lookup tables, or IBLTs, due to Goodrich and Mitzenmacher, and it works as follows. So the data structure is just a table of cells, where each cell contains a counts field and a keysum field. Okay, and the count field just stores what it sounds like. It stores all of the items that, it counts all of the items currently sort of living in the cell. And the keysum field stores the sum of all of the identifiers or keys of the items sort of living in the cell. Okay, so when a new stream item is inserted, we just hash it to R different cells, where R is some parameter of the data structure, and we just adjust the count and key sum fields of that cell accordingly. Right, so if we're doing an insertion, then for each of these R cells, we just add one to the count field and add the identifier of the item to the key sum field. And if it's a deletion, you just do the inverse. Okay. Is the data structure clear, like how inserts and deletes are processed? All right, so how do you do the listing if when it's time to list everything that's sitting stored in the IBLT? So call a cell pure if its count equals 1, okay, which means it's storing a single item. So if it is pure, then that identifier is just living in the key sum field. So just if you find a pure cell, return the key sum field, and then delete the cell. Sorry, delete the item from all of the other cells it lives in, and just iterate. All right, so this is really just peeling. And the point is that every time you find a pure cell and you call delete on the item it contains, you might create new pure cells, and you can just continue. And the whole point of assuming that each item only at frequency 1, at most 1, is that it's very easy to detect pure cells here, but in general, even if that's not the case, you can do it just by keeping some checksums around. Okay, and this is really just peeling on a random hypergraph, peeling to the 2-core. You get stuck in listing fails if the 2-core is not empty. So in this hypergraph, cells of the IBLT correspond to vertices in the hypergraph, and items living in the IBLT are like hyperedges.
But you had some sparsity assumption, right? So couldn't you just argue that even without peeling, most of the items would be isolated?
So the question is how many cells are in your table. So you would need super constant in M number of cells to guarantee that, I think, if you want 1 minus little o1 probability. Anyway. So there's no log. In bit complexity, there certainly is. But in terms of number of cells you need for, anyway, what I can say for sure is that if you do the peeling, then constant factor. So we'll see that in a second. Okay. But the items in the IBLT, living in the IBLT, correspond to hyperedges in the graph, and the cell is pure if and only if the node that it corresponds to in the graph has degree exactly 1. And that's why you're peeling to the 2-core. Okay, and note that in this application, the graph is R uniform. So we're going to just talk about R uniform hypergraphs for the whole talk. Okay, and any questions about this? Great. All right, so you can ask now, if you want to guarantee successful decoding with high probability, how many cells do you need? Because that's like the space complexity of your data structure. This is equivalent to asking, if you have a random R uniform hypergraph, how many edges can you tolerate and still have an empty k-core, 2-core, with high probability? So it's known that actually the appearance of a non-empty k-core in these random hypergraphs obeys a sharp threshold, which means that there's some constant c sub kr. So the constant depends on this, if you're looking for a k-core, 2, 3, 4 core, it depends on that value of k, and it also depends on r, that is how many, each edge in the hypergraph, how many nodes it contains. Okay, so there's some constant, CKR, so that when the edge density is less than CKR, meaning that the total number of edges is less than CKR times the number of nodes, then the k-core is empty with probability 1 minus little o1. And as soon as the number of edges is more than a constant factor larger than this threshold, then the k-core will be non-empty with probability 1 minus little o1. Does that statement make sense? Okay, so what it means is that if you want to make sure that listing in this IBLT will succeed with probability 1 minus little o1, you need a constant factor more than m over this threshold constant number of cells, where m is the number of items you want to be prepared to recover or list. Okay, and these constants are very well understood and they're very reasonable as well. So here are some examples. And they actually have an analytic expression, if you can make this out. It's not important what it is, it's just very well understood. This is sort of derived from Poisson distributions by studying various branching processes. And this is a somewhat old work at this point, and it's perfectly well understood. Okay. So back to, I'll get to the parallel peeling algorithms as soon as I quickly mention some other applications, algorithmic applications of these kinds of algorithms. So low density parity check codes, for the erasure channel, the decoding algorithm in low density parity check codes is exactly peeling on a corresponding hypergraph. And these codes are they are rate achieving. They achieve the rate of the erasure channel, and they have linear time encoding and decoding. So there are also some other error correcting codes developed more recently, which don't obtain new asymptotic bounds, but they use IBLTs directly, and they're very simple and fast to run, encoding and decoding. Also, k-wise independent hash families with constant evaluation time. Some sparse fast Fourier transform algorithms developed in the last few years, cuckoo hashing, and various well-studied algorithms for SAT solving in random SAT instances. These are all peeling on a corresponding hypergraph. Okay. So what this means is that if we want to develop parallel versions of these algorithms, we really just need to understand parallel versions of peeling on these hypergraphs. All right, so let's try to do that. Right, so how would you try to parallelize this peeling process? Well, there's only really one way to do it, and it's pretty brain dead. So every time you want to, rather than sequentially looking at nodes of a less than degree k, just look at all nodes in parallel and peel away all of the nodes of degree less than k and their incident edges and just repeat. So very simple algorithm. Now you can ask, well, how many rounds of peeling does it take? Because that'll be the parallel runtime, more or less. So the algorithm is simple, but the analysis is interesting. And the rest of the talk will be about the analysis, or actually mostly just what the analysis reveals. Okay, so people understand the parallel peeling algorithm? Okay. So what we find is that there are two behaviors. So if you have a random hypergraph where the edge density is less than this threshold for appearance of a non-empty k-core, then you only need order log n rounds of peeling before you actually get to an empty graph because there is no k-core. If you're above the edge density threshold, so the k-core is non-empty with high probability, then you need log n rounds of peeling. That's actually tight. So both of these are tight. So this is great, actually, because most of these data structures should be designed with the k-core to be empty. So nature has put us typically in the setting where we only need log n rounds. Okay. So this implies polylog n time with n polylog n work algorithms, parallel algorithms for listing elements in an IBLT, decoding LDPC codes for the erasure channel, et cetera. And to our knowledge, these are the first such parallel algorithms for these applications. Okay, so in a little more detail, this might be a little small, but the point of this slide is that our upper bound is tight up to an additive constant. So the correct leading constant in front of the log n, if you're in the below the threshold case, is 1 over log r minus 1 times k minus 1. And in a minute, I'll give some intuition for why this is the right constant. So we understand this perfectly well. And then in the lower bound case, I just wanted to mention that our log n lower bound matches an earlier log n upper bound due to Aklioptis and Malloy. They were actually motivated by understanding the solution space of random satisfiability instances and not by algorithms, but turned out that our lower bound matches their upper bound. Okay, so I just want to briefly sketch like a crude caricature of why you might expect the leading constant to be 1 over k minus 1 times r minus 1. So if you let lambda sub I denote the probability a given vertex survives I rounds of peeling, the key claim is that lambda I plus 1 is bounded above by some constant times lambda I raised to the power k minus 1 times r minus 1. Right, that's the key claim. So if you believe this claim, then sort of the right leading constant is precisely 1 minus k minus 1 times 1 over k minus 1 times r minus 1. What basically happens in the peeling process is that after a constant number of rounds, the probability a given node survives is below some constant. And once you hit that point, things start falling doubly exponentially quickly, where sort of the exponent in the exponent is k minus 1 times r minus 1. And that's where you get that constant. Okay, so why should you, let me sort of sketch the claim. Note that node V, any node V, survives round I plus 1 of peeling only if it has at least k incident edges in round I. That's just the definition of peeling. So call these edges E1 to EK, and let's just fix one of them, because we're eventually going to, in this crude sketch, this isn't really what we actually do. Let's just say we can ultimately union bound over all of these if there are multiple k tuples of edges incident to it. So fix this k tuple, and let's assume that no node other than V appears in more than one of these edges. Okay, something close to that will actually happen with high probability, but this won't quite be true, but let's just assume it's true. And then what that means is that there's k times r minus 1 distinct nodes other than V appearing in these edges. Okay, there are k such edges, and there are r minus 1 distinct nodes other than V in each of them. All right, and all of these edges survive round I of peeling only if all of these nodes survive I rounds of peeling. Because if even one of these nodes gets removed, then the incident edge gets removed as well. Okay. So we need all k times r minus 1 of these nodes to survive round I of peeling. And let's pretend that the survival of these nodes are independent events. They won't be. But I'm just trying to say why you might expect this kind of claim to hold. All right, but once you make this assumption, things are pretty straightforward. The probability that all of these nodes survive round I is just lambda I to the k times r minus 1. All right, and let's imagine that this then drives the probability that node I survives sufficiently low that you can union bound over as necessary because here we had just fixed a single k tuple of edges, and it doesn't asymptotically affect the claim. So this doesn't indicate why the right constant is k minus 1 times r minus 1 and not k times r minus 1, and I sort of want to hide that. I mean, the 2-second answer is that this argument sort of has baked into it the fact that all of these nodes already have at least one edge incident to them, namely the one containing it. So they don't really need to survive I rounds of peeling for peeling to a k core. They only kind of need to survive peeling to a k minus 1 core, and that's why k minus 1 comes in there. All right, so that's a crude sketch, and if you understood some of it, great, and if not, well, I'm as tired as you are. So, okay, so here are some simulation results. So we have a 4 uniform hypergraph in the simulation where we're peeling to the 2 core, and this constant C is the edge density in the graph. So the threshold here is 0.772 or so. Okay, so you can see when the actual threshold is significantly edge density is significantly below the threshold, then there are not very many rounds of peeling required, and even more importantly, it grows extremely slowly. So if you have a graph with 10,000 nodes, it takes 12.5 rounds, but even if you go up to 2.5 million, it's still only 13 rounds. So that is like log n. If you are above the threshold, then you won't succeed with high probability. That's already well understood, and you can see that more rounds are required, and it grows faster. That's like log n.
Failed list still edge path.
What's that?
What's the meaning of failed list?
Oh, failed, yeah, it means that the k core was non-empty. Yeah. And then if you're somewhat closer to the threshold, well, it's still growing very slowly, but you can see that you require almost twice as many rounds. So the asymptotic growth is still like log n, but there's some constant in there that depends on the fact that while you are a constant factor less than the threshold, you are not that big a constant factor less than the threshold. So you can ask, well, what is the dependence on how far you are from the threshold? What we find, we give a more refined analysis that says that this leading constant is like order square root of 1 over your distance from the threshold. Okay, so this only holds, it's like sort of a weird number of quantifiers here. If your distance from the threshold is constant, then this statement holds, but the statement is still asymptotic. But the constant that's hidden here now does not depend on your distance from the threshold anyway. Okay, so the main point, though, is that the proof of this result obtains a very refined understanding of the peeling process. So here's a graph of the progress of the peeling process when the edge density is 0.77, which is 2,000ths from the threshold, and here it is when the edge density is less than 2,000 from the threshold, but still less than it. And I'm not really telling you what the y-axis is, just understand it's some measure of the progress. It would take a little bit to define. And so what you see here is that progress sort of falls into 3 stages. So initially, you make a lot of progress very quickly, and then you approach some sort of like threshold number here. It's not so important what that threshold is, like what's going on here, but that's where it takes a while. And this phase actually takes number of rounds proportional to 1 over square root of your distance from the threshold. That's where all the time is spent. And then you get below the relevant threshold or constant or whatever, and then you fall doubly exponentially quickly. So that's what's going on. So just to summarize, there are 3 stages that the process goes through. The first stage, you fall very quickly until you get close to some quantity. In the second stage, you take a long time. This is where the 1 over square root of gap from the threshold comes in, and you make very slow progress, but you then get below this bottleneck, and that's when the original analysis kicks in, and you fall doubly exponentially quickly. So if you remember in the original analysis, I said like it takes constant rounds to get below like 1 over 2 times, this constant that went into the analysis there, and only then do you start falling doubly exponentially quickly.
Square root is because of k equals 2. Or is this?
No. Yeah, this is for all k. Yeah. Okay. I'm just going to finish up now and mention that we actually implemented this on GPUs, and you do see decent speed ups, roughly a factor 20 speed up or so in the listing time. There are some implementation issues that arise when you actually sit down and you realize that, when you go to recover an item, you might actually sort of try to recover it twice in parallel. You have to avoid that. So you can do that by sort of breaking things into serial sub-rounds, and you might be concerned that that will create, blow up the serial runtime by a large factor, where the large factor is just R, the number of cells you hash to. But it turns out that you can analyze that process a little more precisely and find that it doesn't blow up your runtime by a factor of R, it blows it up by like log R. Of course, R is like 3 or 4, so the difference between R and log R is like 2, but maybe you care. And I'll stop there. So in conclusion, a lot of these algorithms in a variety of applications are really just peeling on a hypergraph. And it turns out that you can parallelize the peeling process in a brain-dead way, and you actually get real speed-ups, and that's where I'll stop. Thank you.